I had problem with this when you remove a transformer, which is really important for us. So I was connecting it up with the 5 equivalent circuits. There's no need to do that. So I've edited the nodes. It's removed from comparing it to the 5 equivalent circuits. It just stands alone. It's much easier, and you can just, so I've rewritten that, and I'll be sending that out, I guess, when we end the chapter. It's a long chapter. Yeah, there's no problem there. It's correct. There's no problem. Okay, and then I'll be sending out quiz 2. I think I'm calling it 2A. There'll be 2 quizzes on chapter 2 because it's a long chapter. Okay? All right. So let's look at these problems. These are ones that I cooked up. Next week we'll be looking at a couple problems in the book. All right. I edit this time, and I'll probably keep doing this like last quarter. I edited the problem set before and sent it out to you. All right? I hope that's okay. And send it to Gene too. Gene will replace the existing one on Sakai. That's what we did last quarter. I also made one slight correction in the problem set assignments. And I'll talk about that. That's the problem D today. And we'll talk about that when I get to it. Just one word. I added one word, so you don't need to reprint that, the problem set assignment. But I just thought I should keep it updated. I just felt that I was asking for trouble if I didn't. Okay, so let's look at the first problem. Here it is. We talked about this in class. This is an electrical circuit, purely electrical circuit. And the A, B, and C are these arbitrary impedances here. And the fact that they're impedances, and of course they're amplitude independent. This is a linear circuit. Okay, this is all linear because it has to do with reciprocity. In fact, you know, almost this whole course is linear. We'll talk a little bit about nonlinear effects, but very little. So it's a linear electrical circuit. A is the impedance of this element, B here, C there. And we want to explicitly show that reciprocity holds for this circuit. And what does that mean? Reciprocity means that the transfer impedance here, when we drive here and look at the response, drive, and that means with a voltage, and look at the response, which means with a current here. When we look at the ratio, this will be proportional to V1 because it's linear. When we look at the ratio, which is independent of the voltages and the currents, it should be the same compared to the case if we drive it over here and look at the current over there. That's what reciprocity means here. So the best way to do this, and I mentioned this briefly in class, and I saw you guys are, I think, familiar with this. I saw some heads going up and down, is to do this in steps. And by that what I mean is, the first thing is, what does this voltage source here sees an equivalent impedance? Okay? In other words, it can't tell a difference. It doesn't know the details of this circuit. All it knows is what the equivalent impedance is. And the equivalent impedance is we have this impedance in series with the sub-equivalent impedance here. We know that 2 impedances in series add. So I add A to the impedance across here, and the equivalent impedance of 2 impedances in parallel is we just add them in reciprocal. So 1 over the equivalent impedance, let me call this B, I don't know what to call this. 1 over the equivalent impedance of this is 1 over B plus 1 over C. So therefore, and I've written it right in here, okay, and you got to remember this is 1 over 1 over, so when we clearly did not simplify this, we multiply through by BC, we get this. So this is the equivalent impedance across these 2 points right here. The equivalent impedance across here, which is what the source sees, is just going to be the sum, so we get this. Now we can simplify this, put it under a common denominator. You can see I've multiplied by B plus C here, and we get this expression right here. Why do we do that? Well, we do it because we can now find the current delivered by the source, the current going through here, and of course coming in here. It will be given through the equivalent impedance. Essentially Ohm's law for the equivalent impedance. So we know the voltage, we now know this, the current has to be given such that it satisfies this equation. So the current's given by this. Now it's tempting to substitute in ZEQ here, but we have to carry it along the whole calculation. It's better not to do it. It's better to wait until the end. So let's just leave it like that. So now that we have the current, what can we do? What's the next step? We now know the current going through this impedance.
Find the voltage drop.
Now we know the voltage drop across here. It's just going to be the impedance A times the current. And we know the current now. So we get the voltage drop across here. The reason that's important is now we know what the voltage drop across here is going to be. It's going to be V1 minus the voltage drop across here by the loop rule. So that's what I've written here. The voltage across A, is this. And then the voltage across BC, the combination, is the drive voltage minus VA. So we substitute quantities here, do a little simplifications, all proportional to V1, got to be linear circuit. Now, finally, if we know the voltage across BC, we can find the current through here, which is the same as the current there. And that's what we're after. And at the end, it's just Ohm's law. So I take that voltage that we just found, set it equal to the impedance, and that's the current through the impedance. So I can solve for that, substitute in what VBC is, and I get this. The transfer impedance is the ratio I2 to V1. Okay, and you can see it doesn't involve any excitation here, any voltage or current, because it's a linear circuit. It just depends upon the impedances. And now finally we substitute ZEQ. I just rewrote this here. We substitute that and we get this, and that's what we have temporarily. We want to simplify, of course, but I want to point something out here. Reciprocity means, as we discussed in class, when the transfer impedance is symmetric, so I interchange the drive and the response, and I get the same quantity. It's equivalent. We don't have to resolve the problem. We just interchange A and B. If I want to get the reciprocal situation here, all I do is just interchange A and B. So I want you to look at this expression that we have here. Is it obvious that it is invariant under interchange of A and B? Oops. Do you think if you interchange A and B, you're going to get the same expression? It's not obvious. Okay, so, but what is obvious is we should simplify this. So, I'm sorry, I'm looking up here. So here's the expression. It's not obvious that when you interchange A and B that you get the same value. Physicists call that invariant under interchange of A and B, okay? So, obviously what we should do is simplify this. So bring this under a common denominator. I'll let you verify this. And in the end, we get what I quoted in the lecture notes. And this is, physicists say it's manifestly invariant under interchange of A and B. Okay, it's obviously, you can see it. When you interchange A and B, you get the same, you're not changing it, the value of the transfer impedance. So this proves reciprocity for this circuit. And in fact, it can be shown, and I have to tell you, I've never seen a proof, but it's known, it's well known that reciprocity is true for any linear, purely electrical circuit. I say purely electrical because this is no mechanical stuff going on. We know that when you add mechanical stuff, which is the purpose of electroacoustic transduction, it doesn't necessarily have to be reciprocal, right? It could be anti-reciprocal, for example. Okay, so that's simple. What's interesting here, I think, is that this is take some effort to prove that. It's kind of surprising. So it's simple. Any questions? Okay. The next problem is, this is also related to the lecture. You remember, we looked at the schematic representation of a transducer, 2 double port transducer. And what reciprocity means there is, again, the transfer impedance is symmetric. So we look at on the left side, the electrical side, thinking of that as the drive, we look at the voltage divided by the response, which is now the velocity, and we have to short that terminal there. So that's what that means. That has to equal the transfer impedance going the other way. So this is where we drive. The drive is the force, the response is the current, and now we have to short that to make this have sense. We got those 2 terminals there. We got to short the terminals. That's what that means. And I mentioned to you that when you assume this is true, it's not always true. When you assume it's true, you can show that the transduction coefficients are the same. Okay? In other words, they're symmetric. TEM equals TME. So we want to prove that. That's the purpose of this problem. And this is surprising. It's surprising. There's a surprise here. So here's what we do. We impose this condition on the canonical transduction equations, arbitrary, for any TME and TEM. So we do just what it says. We take the ratio of V over U. So the natural thing to do is look at this equation, divide by U, and then set F equals 0. Well, there's no F there. Okay? So when we divide by U and we have this ratio, this is just a constant, TEM. When we have this ratio, the meaning of this is, for this to be correct, we have to set F equals 0. So how do we handle this? Well, it doesn't take you long to figure out. You got to look at the next equation. Form the ratio I over U for F is equal to 0. So you can see we can find that ratio. We substitute it in, and now we've analyzed the left side of the reciprocity relationship. Okay, we get this. You do the similar thing to the right side. You take the force divided by the current for no voltage. Find the ratio from this is very similar. All right, and you get this. And then we set those 2 things equal, and we get this. And now it turns out, I did this in retrospect, it turns out this is sufficiently complicated that we want to ease the notation here. So the product, we're setting this equal to this. And you can see it only depends upon the product of ZM and ZE. It doesn't depend individually on ZM and ZE. So let's call that something. I'm going to call it zeta, the product of ZE and ZM. And also, I don't want to carry around subscripts here, so I'm going to let X be TEM and Y be TME. Okay, so when I set these 2 things equal and do this ease of notation here, here's what we get. Now, what we want to prove is that the transduction coefficients are equal, which means X equals Y. Is that a solution to this equation? It's obviously a solution, right? It's manifestly a joking. It's obviously a solution, right? If I said X equals Y, I can cancel this. It works. The interesting thing here that's surprising, I haven't seen it in any other book, is it may not be the only solution, right? So Because look, you know, this has some x and y's downstairs. This looks like maybe, you know, a quadratic kind of type of situation where we could have more than one solution. So let's look at that. Let's clear this out. Let's, what am I going to do here? What I'm going to do is I'm going to move x and y. I'm going to beat on this a little bit. Move y over here. Move this term here over there, as you can see. Factor out as zeta. And now I can put this under a common denominator. And so this is the equation. This is the right equation to deal with here. And I probably only got to here by fiddling around with it, okay? Now, x equals y is clearly a solution. We get 0 is equal to 0. But suppose, let's look for another solution. So let's suppose that x does not equal y. If x equals y, I just get 0 equals 0. If x does not equal y, I can cancel x minus y from each side of the equation if it does not equal 0. And then I get this equation right here. As you can see, if I cancel these, I get that. So what that means is we have the solution of the thing we're looking for. We have this other possible solution, which is this right here. If we go back and substitute where x and y and zeta are, we get this. Now, look at this. Usually when you think of a transducer, these are independent quantities. You know, the transduction coefficients or coefficient, there's really only one here, but it doesn't matter. They're independent. So it's unlikely that you're going to have, it would be a coincidence if this were satisfied. However, let's not forget these are functions of frequency. You're sweeping over, let's say, a huge frequency range. It could happen that at some frequency or frequencies, this equality holds, right? So we're being rigorous about this. So it looks like we have this annoying little thing here that you know, we have one possible solution to have a reciprocal transducer is to have TME equal to TEM. But there's another possibility that if this is true, it's going to be reciprocal. However, this is no good. All right. So I remember I was really disappointed at this point, and I started to think about it. Look at this. Look at that. Okay. See that? Now come up here and imagine this is a vector. And there, you see the matrix here? I wrote that on the board. You can see this is a vector. There's a vector IU, and you see that matrix there? If this is true, what does that mean about the matrix? This is like really important in linear algebra. If ZE times ZM equals TME times TEM,
the determinant is 0.
The determinant is 0. That means we can't invert this. That means for a voltage, for a given voltage and force, we can't find a current and a velocity. That's unphysical. That's unphysical. So we're saved by that. Surprising. We can't have that. If we had this, we would have an unphysical transducer. You know, for a given current and whatever it is, for a given, however we view it here, for a given force, for a given voltage and force, we have to be able to find that there's going to be a unique current and velocity. So we rule it out. So it's kind of interesting. We're saved by that, and we end up with this. Okay, any questions about that? Surprising. Okay, I don't know why I'm rushing. I think we have plenty of time. But I'm concerned about the last problem. Okay. So we have the infamous 5 circuits. They look very different, but they're all equivalent to each other. and they're equivalent to the transduction equations for a when TEM equals TME, to the reciprocal canonical transduction equations. The one that we haven't addressed yet, we've addressed 4 out of the 5. If you go back and think about it or go back and look, it's C. It's the third one. We haven't shown that that's equivalent. So the problem here is it to show that it's I'm getting confused with it because I just looked at the quiz. Oh yeah, so we're going to show that this is equivalent, okay, to the canonical transduction equations, just like we did directly or essentially for the other ones. Can't remember. So here it is. Okay, it's got these 3 loops here. There's this turns ratio, which is really in general a complex dimensional number. Okay, this. We have the voltage here, the force here, some current here, some velocity here. And now I want to show that this is equivalent to the transduction equations. So what we have to do here, and I think I mentioned this yesterday or the day before, we're going to assign usual mesh current here. We're going to assign an unknown I prime there. And now, because we've got this impedance in the way, this is not going to be V, we're going to call it V prime. We're going to call that V prime. We want to introduce these 2 unknowns, which we're going to have to eliminate, obviously, because in the canonical transduction equations, it only involves V, F, I, and U, in addition to the parameters, you know, the circuit parameters here. Okay, so what I see here, the first thing is, I know, everybody knows, kids know this. I knew this, well, we had electric trains when I was a kid. That was like computers, or, you know, it was big. It was really important. You had to have an electric train when you were a kid. So, so we had their transformers there, and we all, you know, wanted to know what's going on there. And our fathers, back then, mothers were housewives. Okay, so the mothers would say, "Oh, there's a transformer in there." Well, what's a transformer? Well, so that's why I learned about a transformer. I was a little kid and I had no idea what was going on. It's just that when you had more turns here, it stepped up the voltage. Okay, so we know the voltage across here. It's going to be just this turns ratio, this number times that voltage. Okay? And again, we're thinking of this, it's really actually mechanical, but because this is not a dimensionless number, but that's okay. So I think I wrote this in here. Here's the turns ratio. So the voltage here is going to be boosted by N or depleted or reduced. So we know the voltage here. Okay, so let's go ahead and write down the equations now. For the left loop here, I have this voltage here has to be the voltage drop across here. And you see these 2 currents coming in here. So I get this. That's Kirchhoff's loop rule for here, for this loop, using the balance idea here. Let's stay away from this. Let's go over here. We think of this as a voltage. It has to be equal to the drops. The drop along here, which is just this, and then the drop along, we have a voltage this way, but what we're after is the drop. So it's a positive, we don't put a minus sign here. Now I have to say, you need to be careful about the signs here. And sometimes at this point, I have to admit, when I get in trouble with the signs, it's often best not to think of the balance thing here. It's best to go back to Kirchhoff's rule and sum all of the voltage changes and set it equal to 0. Don't do this balance trick. I think the balance trick, to me, makes life much easier. But nothing's perfect. So when you're worried about signs, I usually get rid of this, and I just do the strict go through and say, okay, is this a positive voltage change or a negative voltage change? And go around the whole loop and set the sum equal to 0. Got it? Okay? You can do it however you want to. But here, I know this is voltage. I'm looking at the drop, so there's no minus sign there. This is right. Okay. Now, the problem here, of course, is that we got to get rid of I prime and V prime. Well, V prime we know. We know, no, we don't know V prime. So, I'm sorry. I got confused. I was thinking of that. Okay, so let's look at this. I've got this I prime here. I know there's going to be a relationship between these two currents here. This current U is going to be down by a factor of N from I. Right? It's the opposite. Instead, it steps up the voltage, let's say, it steps down the current, and vice versa. So that gives me this right here. Okay, and I've substituted what N is. So we can find I prime. How do we get V prime? Well, we're kind of stuck here. We actually have to take this, substitute it into here. We have to go to our equations. And now you can see we can find, excuse me. Oh. God, I'm sorry. We haven't done the middle loop. We haven't enforced Kirchhoff's laws here. We need to do the middle loop. So we apply Kirchhoff's law to the middle loop here. Now we don't have to deal with this because the voltage across here is just given by that. So you can forget this. You can actually do Kirchhoff's, you can actually take this to be the loop. It's simpler. So what I see here is, this must be the voltage drop across here. Uh-oh, I got a minus sign here, right? So I got to include that. But you'll notice the current's going the opposite direction. So those two minus signs cancel for the voltage drop. Again, you want to be careful with this. They're gonna cancel. It's going to end up being positive. And then I get the V prime, which is what we're after. So we know I prime. Here it is. I can substitute that into here. And I did it right here. And I can solve for V prime. So we get V prime. Now we're essentially done. We take V prime, put it into here, take I prime, put it into there. And these two equations become, the primed variables are gone. We get this, the first equation, this, multiply through, yep, that's the first canonical equation. V equals, that's the first one, right? You recognize it for a reciprocal transducer. The second one, a little bit of algebra, cancellation, and that's right, F equals, that's right. So we've confirmed that the third of those 5 circuits is equivalent to the transduction equations for a reciprocal transducer. Questions, yeah?
I'm having a hard time seeing the second, how you got the force loop.
This one?
Yeah.
Okay, so again, we think of it electrically, right?
Right.
So this voltage has to be balanced by the drop here. The drop is just the current times the impedance times the current. And then we've got to look at the drop here. There's a V, oh, it's a sign? Is the sign, is that what you're, okay. So the voltage across here is upward.
Okay.
So if you think of it, positive is upward.
Okay.
So the drop is going to be, if it is positive, which means the voltage is increasing going from here to here, then the drop is positive.
Okay.
Right, when we go across a resistor, I've got a current here in this resistor. What's the voltage drop? It's I times R.
Right.
Okay, it's not minus time. You know, it is the drop. The negative is in the drop. The voltage decreases by IR.
So if you did the sum like you were talking about, set it equal to 0, it would be F minus UZM plus V prime, right?
Okay. No, it's minus.
Minus. Okay.
Because if there's a positive, assuming a positive voltage here, this is a drop. The voltage is decreasing, so you got to have a minus sign in front of it. So you get the same answer, right? We all agree? Yeah. And you know, this is just however you want to handle this. You know, I have to admit, I like this drop idea. You know, I like to not deal with these negative signs. But like I told you, when I get into trouble, I go through and very carefully sum all the voltages with plus and minus signs and set it equal to 0. But it doesn't happen that often. Okay? Yeah. Yeah, this is something that you know, is absolutely critical for a transducer. So if you make a mistake of a sign here, that could just cause all kinds of trouble. So if you're worried about, you know, like I said, if you're ever worried about it, I would just carefully go through and sum all the voltages here. This one has the same, this is n times that, and up is the positive way, you know, is the positive way. So when you go across here, there's a negative change in voltage when you go from here to here, which means the drop is positive. If you don't like drop, you can just not use drops at all. You can just sum the change in voltage.
Can you just write out the sum on the board and like show me like explicitly what
for this side, right?
Yeah,
okay, I'm
just having a hard time seeing.
I go from here to here. This is the positive direction. So what's the change in voltage? We're going to do this, right? So I get F. Okay, and F can be positive. When F is positive, I do get an increase. When it's negative, it's negative. So it works for both signs. And then what happens here? Well, here I'm going in the direction of the current, so I'm going to lose. It's going to be a voltage drop for a positive U. So it's going to be ZMU. And of course, if U happens to be negative, it's going to change the sign. So everything works out. It's general. Then when I go here, there's a voltage going up this way. That's the positive direction. So I'm going to get a drop. This voltage, when it's positive, this is going to be at a higher voltage than this. So the change in voltage will be negative. And what is the value of the voltage here?
Oh, it's V prime times the transducer.
Yeah, so let me just write it like this.
Okay.
Can everybody see that? Yeah. Yeah, this is a problem.
I see what I was, the arrow on the other side was throwing me off.
Yeah, now every year when I teach this, I have to think, this gets back to the basic relations for a transformer. If I've got a positive voltage here that's increasing, is it increasing, is it up or down there? That you got to go back to the induction to a transformer. It turns out to be up. So it turns out that what's in the lecture notes is correct. I carefully checked those errors. I've done it a number of times. If you think back to the lecture notes for when we just focused on a transformer and we looked at the voltage and currents change, those arrows there's meaning there, and you have to respect those. Or you could introduce or remove a minus sign in the loop rule. Yeah, and I thought about it when I was looking this over. I was thinking, oh, wait a minute, yeah, it's right. That's why I used the word upward here to help out. It's supposed to help. Okay, good. Any questions? Any other questions? Okay, so when I was preparing this course, I felt there had to be some problem on the electrostatic, you know, that problem we did showing that the electrostatic transducer is reciprocal. So I start to think of a sphere. So that's the subject of this. We're going to look at we have a sphere. It could be like, you can imagine like a racquetball that's been painted in conducting paint. Okay? Racquetballs exist. Conducting paint. I know that. I still have some. And conducting paint exists, and you guys have never seen it, but you know it exists. Silver paint, typically silver paint. So you get this conducting sphere, and what you can do here is you can put a charge on there. Now, if it's not going to really be, Well, I guess it is going to be relevant because we're going to talk about the capacitance. So the way people think about this, they think of this as a capacitor. You know, it's holding charge. It's a capacitor. The problem is, where's the other plate? Because capacitors are supposed to have two plates, right? Oh, and when we talk about capacitors and we use the word plate, it doesn't necessarily be a flat plate. It's a conductor. We really should say conductor. Where's the other conductor? Well, we're free to imagine it to be at a concentric sphere at infinity here. Concentric conducting sphere at infinity. At infinity, for a localized charge distribution, we'll call that zero voltage. So the voltage on this other plate, this other conductor, is going to be zero. So we hook our supply up like this. You can think of this as actually going to this big, infinitely far away, infinite radius sphere. So we do have a capacitor here. And the next thing I'm going to say is, you know it's coming. If you oscillate, there's going to be some voltage here, some equilibrium voltage. We use, like we did in class, 0 to denote the equilibrium values. If I oscillate that, what's going to happen? When more positive charge goes on there, what happens? All those positive charges are repelling each other, right? So what's going to happen? And we have a compliant sphere, racquetball. It's going to expand, right? When the charge is less, it's going to contract. So it should, in principle, it should be able to send out sound. So what I just said is just essentially the same thing we said for this. It's just in a different geometry here. What about the other way? I have a sound wave coming in, and go ahead and imagine the very typical situation, which we will, I think, always assume in this class. The sound wave will be small compared to the sensor here. The wavelengths will be large compared to the sensor. Okay? So what is this thing going to see? It's going to see this alternating pressure. Pressure is going to go up from atmospheric pressure due to the sound wave. It'll uniformly go up and down because the wavelength is large. Okay? That's not critical here, but I might as well mention it because we're going to make that assumption, I think, everywhere in this course, that the wavelength is large compared to the sensor. Now, I should say, when you have a bunch of sensors, then the wavelength doesn't necessarily have to be large compared to the size of your array. When you have an array of sensors, and you all probably know this, but I want to say that. But for a single sensor, it's almost always true that the wavelength is large, and that simplifies things, as we'll see. Okay, I'm getting way off track here. All right, so this is this is electrostatic transducer. Appears to be, it can be it's reversible, and so what should be true? What should be true here? If it's electrostatic, I guess I didn't talk about this. Apparently all electrostatic type transducers are reciprocal. Okay, again, I don't know if there can be a general proof of that, but it just seems that they're always reciprocal. And when a magnetic force involves, they all seem to be anti-reciprocal. All right, but we're going to prove that in this case. We're going to prove that this is reciprocal, and we're going to find the we're going to show this by finding the transduction coefficients and showing that they're the same, from mechanical to electrical and electrical to mechanical. Okay, so we go down a similar path that we did in lecture for the this other one, the parallel plate one. Quantities here. Oh, what's the But it's different. It looks, the geometry looks like it has causes a big difference here, and there's a surprise regarding that at the end that you'll see. So what's the voltage of a uniformly charged conducting sphere? I don't know if you guys remember this. It's 1322. It's elementary electromagnetism. It's the charge is proportional to the charge divided by the radius. And we're looking equilibrium here. The equilibrium or ambient radius we're going to call little a. That's very common. So this is the voltage. Does this ring a bell, you guys? It's, again, if you want to look into that, any introductory electromagnetism book, in physics at least, I don't know about engineering, but it'll be in there. So that's going to be our voltage. We're assuming 0 voltage at infinity. This is a common reference choice that people make. And equilibrium means that all of the forces have to balance on this sphere here. Okay, so what forces do we have? Well, we have this repulsive electric force, which exists in equilibrium, and it's always there, right? These charges are trying to get away from each other. So there's a repulsive electric force in equilibrium. What's this? Mechanical. Well, I'm sorry. So I changed the problem set assignment. We want to, for simplicity, we're going to assume that this is evacuated, that there's a vacuum in here. And I'll talk about that at the end, okay, about making it not a vacuum. But I think for us, this is sufficiently complicated that we should call this a vacuum. All right? So, there I can see two mechanical forces here. There's the stiffness of the material, the elastic stiffness, and then there's the, excuse me. I see one mechanical force here. It's just the stiffness. This is going to have some stiffness. When you radially expand or contract, there's going to be a Hooke's law there for small oscillations, right? So that's this. This is going to be the force due to the fluid out here. And for simplicity, like I said, we're going to assume vacuum there. So these have to all balance to be equal. The sum of them all has to be equal to 0. This is always positive. This is always negative. This, I think, could be positive or negative. It depends.
So all the forces have to be 0. So that
in equilibrium.
Oh yes, the sphere is not.
It's in equilibrium. It's not moving. It's just sitting there. So they have to balance by Newton's second law, right? Okay. Now I got to tell you what these forces are here. For example, let's look at this. This is the force due to the fluid on here. Well, technically the force due to the fluid is 0, right? It's when you look at, you got little forces going like this. If you add them all up, what do you get? You get 0. But that's missing the point for us. We're after a transducer here with this thing moving. So by force here, what we mean is the pressure times the area. In other words, we're taking all these individual forces here and adding all the magnitudes. Okay, so that's the purpose of this statement right here. That's what's relevant for us. You know, if you hand somebody a capacitor and you tell them the charge is 0, and they put their hands across there and they kill themselves, and you go to court and you tell the judge, I was thinking about this the other day. You say, the net charge was 0. The charge on the positive plate was the same as the charge on the negative plate. Do you think you'll get off? Do you think you just can walk away? No, I don't think so. Okay, we talk about a charge, the charge on a capacitor. We're talking about one of the charges. Okay, so it's a similar situation here. Technically, we're looking the force here. What's relevant for us is the integral of all the magnitudes. So it's just the pressure times the area. All right. Yeah, physicists think about these things. It's not just me. Okay, physicists are like that. Okay, so we're going, as in class, as in lecture, we have all these fluctuating values. There's all 0 in equilibrium, okay? The voltage, the charge, the displacement, there's that x there, etc. All right? Okay, so here we go. What's the instantaneous voltage on the sphere? Well, from here, it's the total instantaneous charge, and it's the instantaneous radius that's involved down there. So you can see here, when we form that, we get this. This looks familiar, right? And we're only interested in linear oscillations. So we're going to keep this. 1 over 1 plus a small quantity is 1 minus a small quantity. Okay? So that's going to come upstairs, and then I'm neglecting the product here because it's higher order. Remember that? So that's how I get this. Q times X is negligible because they're both tiny. So the product is very tiny, so we neglect it. So the total voltage is the equilibrium plus the fluctuating voltage. This allows us to find the fluctuating voltage. It's right there, times V naught. So there's the fluctuating voltage. Now I'm going to go ahead and switch to, for some reason, I don't know why, we're going to switch to our canonical variables. Instead of current and displacement, we're going to deal, instead of charge and displacement, we're going to deal with current and velocity, because that's what's in the transduction equations. So I introduced I omegas. I think you're familiar with that by now, so that's no problem. Okay, oh, and I've introduced something else here. Q is equal to CV, right, for a capacitor. We have a capacitor. So in equilibrium, it's convenient to use, you'll see why it's convenient in just a moment. It's convenient to use this ratio here. Q naught divided by V naught will be C naught, the equilibrium capacitance. Now, and the reason we introduce it is, what is 1 over I omega C naught? That's the electrical impedance of a capacitor. If we have other electrical impedances around, inductance, resistance, we would just put them into here. So to be precise here, in a blocked situation, we have a purely electrical system. I can generalize this just by letting it become Z capital E. We've done this several times before. It's a nice trick. Okay, so we're generalizing our transducer, which is important if you want to build this, and Faisal's going to build this. I think I mentioned this to you before. This is part of his thesis. We're going to try to make this work as a demonstration. So it's nice to have that general like that. And it also looks a lot nicer, right? and it's part of the canonical equations. So we get this. Now, we can, at this point, we can identify, this is the easy half, the electrical half, which is almost always the case. The electrical side of a transducer is usually easy to handle, and mechanical is where the trouble comes in. You can see that we can identify TEM, mechanical to electrical. Mechanical to electrical, that's TEM. You can see that it's equal to this. And you'll notice that it's negative. So you might be thinking, uh-oh, is this going to be anti-reciprocal? Well, wait, okay. And I can explain that, but this is what we got. So in a sense, we're halfway through. Okay, any questions? So now we've got to look at the mechanical side. And like I said, this causes it's a little bit more difficult here. And this, of course, is Newton's second law. So we're looking, if we look at a little element here of mass on the sphere, the sum of the forces here is going to be the mass times the acceleration. But we have an isotropic situation here. We can go ahead and integrate all of the magnitudes of those the forces and all of the masses, and we can just apply Newton's second law to the whole, to the entire spherical shell. We can immediately go from what the force equals the mass times the acceleration of an element to the whole thing, where now the force is the total force, the integral of the magnitudes of the force. That's what's sitting here. This is the total mass, and this is the radial velocity. We can do that by symmetry. This is we have an I omega, of course. Now, this comes from the elastic stiffness. That's going to be incorporated into the mechanical impedance. Just like we incorporated the capacitor. We're going to assume a general mechanical impedance, like we did a general electrical impedance. Okay? Now, this electrical force, it involves transduction. The electrical force, when there's motion, the electrical force is going to change. Right? So there's transduction in there. So we've got to, we're not going to absorb that into the mechanical. We have to deal with this. This is important. So we can get at it this way. You have a charged sphere. There's a repulsive force. And now, actually, I think this is not part of introductory electromagnetism, but Mark can tell you that there's an electrostatic pressure here. these charges, there's a repulsion force here. And you take the electric field, the force, the total force here is going to be the electric field times the charge divided by 2. There's this famous factor of 2 here. And that's in there, I don't want to get into this, but it's in Griffith's E&M book. Okay? Have all of you had some intermediate level electromagnetism? That's usually, Dan?
Yeah.
Okay. No? Okay.
Remember?
Yeah, that's something you probably don't, I mean, I had to think about it when I first hit it. But, but this is well known, and it's in Griffiths, for example. It's probably not in an introductory book. Probably not. But it's reasonable, okay? You know, you're taking the field, here's the electric field, okay? Here. It's given by that. That's well known from Gauss's law. And the force is going to be the electric field times the charge, and that's what we're doing here. And the factor of 2 is because a charge can't exert a force on itself, it turns out. But if you're interested in that, come by and see me or look in Griffiths. Okay, so once we got that, we can write the force down here. The total instantaneous electric force, I put in the instantaneous charge, the instantaneous, radius. And now again we linearize, right? So I don't need to go, you're well familiar with that. We get this. And now, here's something that's a little confusing. This is the electric force. This value right here, it's going to contribute to the mechanical stiffness. It's not a transduction term. There's no current here. It's not a transduction term. It's simply, due to the electrical charge here, it's going to effectively change the mechanical stiffness. So we incorporate that into Zm, lowercase m. So when we do that, we move all of the impedance, the mechanical impedance stuff, we move it over here, right? What we're left with is the force that we're after. This is the force on the force of the fluid on the transducer, which is important to us because it's going to generate, we're generating sound or picking up sound, so that's important. Here's the transduction term. It comes from right here. Okay? We write this like this. I've generalized, I've put all the mechanical impedances and whatever there may be, dash pots, whatever, it's all in there. We get that. And now, you'll see here, when you bring this over here, it becomes minus, and there's an I omega floating around. So this is our transduction coefficient, and it's identical to the previous one, to the minus sign there. And like I said, I think I understand why the minus sign is there, and you can look in here. We're over. You can look in here. I want to just make one more quick statement here. You can generalize this to put some fluid inside. Okay, it can be pressurized or whatever. It can be different than the fluid outside. In our case, if our transducer, we hope it's going to work in air, because that's a nicer demo. But if it doesn't, we'll have to do it in water. All right, and in that case, we'll have water out here and we'll have air inside there, right? So it can. I made some notes here. It can be generalized, but I thought it would be best in this case just to imagine it to be evacuated. So I hope this works. We're going to find out, and we have a theory to guide us. So that helps. Okay, any questions? Okay.